For more than 100 years, there's been this one scientific theory that's just been a lightning rod for controversy. It's been debated not just in labs, but in classrooms, in courtrooms, and probably in your living room. We are, of course, talking about the theory of evolution.
But here's a thought. What if the real fight isn't even about the evidence for or against evolution? What if it's about something much, much deeper? What science itself actually means? Because the answer to that question doesn't just change this debate. It gets to the very heart of how we know anything at all. Okay, so you see a quote like this, and you're probably thinking, all right, who's the critic? But get this. This wasn't from someone outside the scientific world. These were two biologists, and they published this in the journal Nature. They were arguing that there's something fundamental about the theory of evolution that puts it in a totally different category from other scientific theories.
So to really figure this out, we have to do something a little different. We need to stop looking at the theory for a second and put science itself under the microscope. We have to ask, what are the rules of the game? Because it turns out, not everyone is playing by the same rule book.
All right, first up, let's lay down the law. What's the classic by-the-book definition of what a scientific theory is supposed to be?
So, this is what's known as the hypothetico-deductive model, or the HD model. It sounds complicated, but the idea is actually pretty simple. A real scientific theory isn't just supposed to be a good story about what happened in the past. Nope, it has to be a machine for predicting the future, and in a way that could actually be proven wrong. If you can't test it and potentially prove it's false, then under this strict model, it's not really science.
And to see how this whole thing works in the real world, let's jump in a time machine and go all the way back to 1628. A guy named William Harvey had this totally radical idea about how blood moves around, and it is a perfect example of this HD model in action.
Okay, so check this out. Harvey starts with a big idea. His postulate, blood flows in a circle. Now, from that one idea, he did some math and came up with a mind-blowing deduction. He calculated that the heart would have to pump out 540 pounds of blood an hour. That's way more blood than is in a person, right? So his conclusion? It has to be the same blood circulating over and over. And this led to a really clever, testable prediction. If it's all circulating, then something you put on your feet should eventually show up on your breath. And yeah, they actually tested it with garlic, and it worked. Now that is a powerful predictive theory. So here's the bottom line, the really crucial takeaway. Under this super strict model of science, a theory's real power comes from making these risky, testable predictions about what we will find, not just tidying up and explaining what we've already found. Okay, so now that we have the rulebook, let's bring in the defendant. What happens when we put the theory of evolution on trial using these very same hypothetico-deductive rules? And this, right here, is where things get really controversial. Critics, including some biologists like R.H. Peters, argue that when you really put evolution under this microscope, it just doesn't quite fit the mold. They've got three major challenges.
Challenge number one is the tautology argument. Now, a tautology is basically a statement that's true by definition, so it's circular. Think of it like saying all bachelors are unmarried men. I mean, yeah, that's true, but it doesn't actually predict anything new about the world. And the critics apply this to that famous phrase, survival of the fittest. It sounds scientific, but they argue it's a perfect circle. Think about it. Who survives? The fittest. Okay, and who are the fittest? Well, they're the ones who survived. See? From this angle, it's not a prediction you can test. It's just a definition you can only apply after you already know the outcome. All right, challenge number two gets right to the heart of this HD model, falsifiability. The whole point of a good scientific theory is that it has to be vulnerable. There has to be something you could possibly discover that would prove it wrong. So critics ask a really tough question. What piece of evidence could you find that would actually falsify the entire theory of evolution? They argue because it's so incredibly flexible at explaining almost anything we find, it's almost impossible to imagine a discovery that could truly break it. And they point to some specific things they say are missing, things that would make the theory more believable as a predictive science. For instance, why haven't we ever observed life coming from non-life? Why does the fossil record often show these sudden explosions of new life forms instead of a smooth, gradual change? Now, the point here isn't to say these things disprove evolution, but to argue that their absence makes it hard for the theory to make those specific, falsifiable predictions about what we should be finding. Okay, this
third challenge is maybe the deepest one of all. It's the idea that evolution isn't really functioning as a testable theory anymore, but is what the historian of science Thomas Kuhn called a prevailing paradigm. A paradigm is, well, it's bigger than a theory. It's the whole worldview, the set of glasses a scientist wears that colors how they see all the data. And this right here really shows the clash between two totally different ways of looking at science. In the HD model, your job is to try and break your own theory. You're constantly trying to falsify it. But in the paradigm model, your job is more like puzzle solving. You take any data that doesn't fit, the anomalies, and you try to make it fit into the worldview you already have. The theory isn't something you test, it's a fortress you defend.
And this quote really gets at the heart of that criticism, the fear that a paradigm can get so big, so dominant, that it actually stops people from thinking in new ways. Instead of seeing evidence that contradicts the theory as a major problem, it's just treated as a little puzzle we'll figure out eventually.
So, where does all this leave us? Is evolution unscientific just because it doesn't pass this one specific, super strict test? Or, and this is the big question, maybe the rulebook itself is the problem? This is where the whole debate shifts from just rules to actual revolutions in how we think about science. You see, the core of this whole conflict might not even be about fossils or genetics at all. It's about a deep philosophical disagreement over what science is supposed to be. You've got one side playing by the strict predictive rules of the hypothetico-deductive game, while the other side sees science as this bigger process of building and refining these huge explanatory paradigms. And what's really fascinating is that this isn't just a debate between people who support evolution and those who criticize it. The theory itself is anything but a settled, monolithic dogma.
That's right. Inside the world of biology, there are some pretty fierce debates going on about the mechanisms of evolution. The main idea of common descent is pretty much accepted, but the how it actually happens, that's a super active area of research and disagreement.
So on one side, you've got this idea of the blind watchmaker, which was made famous by Richard Dawkins. It says evolution is basically driven by random chance and unpredictable mutations. But then on the other side, you have scientists who argue that the Earth's own changing chemistry has actually guided evolution down a much more predictable, maybe even an inevitable path.
And as the physicist Harold Morowitz says, there's a kind of quiet paradigm revolution happening right now in biology. This idea of radical randomness is being challenged by a new search for more predictable, almost law-like principles. Now, this isn't a rejection of evolution at all. This is the scientific process, right here in action, refining and challenging its own big ideas. So this brings us to one final, huge question. This whole debate over evolution really pulls back the curtain on a much deeper truth, doesn't it? Science isn't some clean, perfect process of just gathering facts. It's a human thing, shaped by different philosophies, by these powerful paradigms, and by its own internal revolutions. And it forces us all to ask a really fundamental question. How should we approach what we believe to be true when science itself has blind spots and is built on paradigms that can shift? The answer really defines not just one theory, but the entire scientific journey.